Here's a beam that's simply supported by a hinge at point A and a roller at point B. You see a number of forces and a moment acting on this beam as shown here. In this case, we are looking to replace this system with an equivalent resultant force and moment at A. We're going to basically take all the forces and crunch them into one new force applied at point A. We're going to take all of the moments and crunch them into one new moment also applied at point A. The purpose of this activity is to simplify the system. One possible application would be to determine how strong we need to make this particular bolt here. Since there is no assumption or statement of static equilibrium, we can just use a working diagram here. We will need to define our positive directions. We'll also need to label all of our forces. There's no necessary order in which you perform these tasks. I always do the x direction, then the y direction, then the moments. So here's how that looks. I'd say something to the effect of evaluating the original x direction. So I'm going to set up a new variable and I'll call it fxn for the new x force, and that fxn should equal the sum of all the old x forces. Upon inspection, you'll see that f1 and f2 have a 0x component, so fxn is then just left to equal f3x. f3x is a positive 4/5 of f3. Since we did not use static equilibrium to solve this problem, this positive sign indicates actual direction. The third step here is to evaluate the original y. Once again, I'm going to make a new variable called fyn for the new y forces, and it has to equal the sum of all the original y forces. All three of those forces have y components, so they will all remain in my equation. And all three forces are going in the negative direction. Plug in the values in. We find that fyn equals a negative 100 newtons. So now we've evaluated the original x and the original y directions. Next, I'm going to evaluate the original moment. And I'm going to specify the point that I'm evaluating with respect to, which is point A. So I'm going to say MAN for the new moment around point A equals the sum of all the original moments around point A. So that equals F1 times d perpendicular plus F2 times d perpendicular plus F3x times d perpendicular plus F3y times d perpendicular. And don't forget, if there is a moment present, don't forget to add it to this particular equation. Now before we go on, once again we want to see if any of these moment terms are 0. So F1 passes through point A, therefore its perpendicular distance is 0, which means that F1, although there's a force, will not produce a moment. F2 has a non-zero force and a non-zero perpendicular distance. F3's x component actually passes through point A as well, so it produces 0 moment. F3's y component has a perpendicular distance and a non-zero moment, and of course the moment will produce a moment. Now we need to figure out which type of rotation these forces are going to provide. F2 would cause a clockwise type of rotation, which means it's going to be negative, and its perpendicular distance is A. F3y is also going to provide clockwise rotation, and the value of F3y is 3/5 times F3, and its perpendicular distance is A plus B. M1 is already going in the negative direction. Now we can plug our numbers in, and we will find that the new moment around point A is a negative 470 Newton meters. Since this particular problem asked for a single force to replace the entire system with, I'm going to go ahead and draw a new working diagram that shows the x and y forces and the resultant force. Now this working diagram is not required, but I find it helpful to help me know which quadrant FRN, or the new resultant force, is going to be in. Now we can solve for that new resultant force, And I'm first going to solve for the angle theta, which equals the inverse tangent of opposite over adjacent. The opposite side is Fyn. The adjacent side is Fxn. Plug in the values in, we'll find that theta equals 68.20 degrees. Now we can solve for Frn, and we can just use Pythagorean's theorem. And once we plug the values in, we'll find that Frn equals 107.703 newtons. When you write the answer, don't forget to include all of the new things. This problem asked you for resultant force and moment at point A. So Frn equals 107.7 newtons at theta equals 68.20 degrees. The other thing it asked for was the moment. So MAN equals 470 Newton meters going in the clockwise direction. So that is how you simplify a system into a single force and moment.